Hey guys, welcome aboard to Snoozy Voyager. Tonight, we are doing something a little different. No battles, no kings, no plague. Well, actually maybe a little plague. Tonight we're going somewhere truly ancient, somewhere so old, so utterly forgotten, that the world it belonged to doesn't even exist anymore. Not the civilization, not the empire, not the coastlines, not the continent as you know it. We're going to Antarctica, but not the Antarctica you know, not the one that looks like the inside of your freezer after you've forgotten to defrost it for 3 years. No. Tonight we are going to Antarctica before the ice, before the silence, before it became the most inhospitable place on Earth, and the destination of choice for scientists with a very specific kind of personality disorder. So before you get comfortable, take a second to like the video and subscribe, but only if you actually enjoy what I do here. Leave a comment telling me where you're listening from and what time it is for you. I have a feeling it's somewhere between I should be asleep and I deeply regret my life choices. Now dim those lights, flip on a fan, pull that blanket all the way up, and tuck everything in. Yes, everything. Let's take a moment. Have you ever wondered what Antarctica looked like when it was actually warm? Was there really a time when the bottom of the world had forests, rivers, and actual weather worth complaining about? Did creatures wander across a lush southern continent, completely unaware that in a few million years their entire world would be buried under 2 miles of ice? Could you have stood on an ancient Antarctic beach, looked out at a warm sea, and thought, yes, this seems like a perfectly normal place to live? What killed it all? Was it slow? Was it dramatic? Did the continent just quietly freeze over one winter and never thaw out? And what does it mean that we're only now, with satellites and ice cores and an almost alarming amount of scientific stubbornness, beginning to understand what was down there? Congratulations, you've just arrived on the ancient continent of Gondwana. The year's approximately 90 million years ago. The air is warm and thick. Something that sounds suspiciously like a bird is screaming in the distance, and you're standing on land that will one day be called Antarctica, except right now it has trees. Let's start at the very beginning, and the beginning in this case is almost incomprehensibly long ago. Around 500 million years ago, Antarctica was not some frozen wasteland bolted to the bottom of the Earth like a misplaced ice cube. It was part of something much larger, much stranger, and much harder to say, a supercontinent called Gondwana. Picture, if you will, a single enormous landmass containing what would eventually become Antarctica, South America, Africa, India, and Australia, all smooshed together in one slow-moving geological huddle, drifting around the planet like a very large, very confused raft. You're standing at the centre of the ancient world. The ice, the penguins, the research stations, the frozen tundra, none of it exists yet. What exists instead is warm rock, shallow seas lapping at unfamiliar coastlines, and the very early stirrings of life beginning to figure out what it wants to be. The ground beneath your feet is ancient. Not old in the way that a cathedral is old, or a Roman road is old. Old in the way that makes those things seem like they were built last Tuesday. The rocks of Antarctica contain some of the oldest material on Earth's surface, formed in a time so remote that the continents themselves had not yet arranged themselves into anything a modern geographer would recognize. If you had a map of the world from 500 million years ago, you would stare at it for a long time and feel nothing but confusion. The coastlines are wrong. The oceans are in the wrong places. The land masses look like someone knocked over a puzzle and just left it. And yet, in a way that is both comforting and slightly unsettling, the laws of nature are exactly the same. The sun rises and sets, gravity works, water runs downhill. Life, wherever it can get a foothold, and clings and adapts and multiplies. The early world of Antarctica is not an alien planet, it is this planet at an earlier draft, before the revisions, before the ice got its hands on it and rewrote everything. What you need to understand, above all else, is that nothing about Antarctica's frozen present was inevitable. The ice did not have to happen. There was no cosmic rule that said the bottom of the world must be uninhabitable. For most of the Earth's history it wasn't. The warmth was the default. The freezing was the exception. And the exceptional thing about that exception is how completely it erased what came before. You could walk across Antarctica today and find no obvious trace of the forests, the rivers, the creatures, the warmth. You would see white, you would feel cold. You would wonder, quite reasonably, how anyone could survive out here for 10 minutes, let alone how entire ecosystems thrived for hundreds of millions of years. But they did. The evidence is there, buried under the ice, pressed into the rock, locked in fossil beds that scientists have spent decades extracting with cold fingers and tremendous patience. Antarctica was alive. It was warm. It was full. And then, with the slow, merciless efficiency of deep geological time, it was buried. The world beneath the ice is not a myth. It is a graveyard, and a remarkably well-preserved one. What lies down there is the story of a continent that had everything, kept it for an almost unimaginable length of time, and then lost it to the cold. It didn't even get a warning. One day, geologically speaking, the forests were there, and then, millions of years later, they were not. Nah, the ice doesn't negotiate. Let's talk about Gondwana, because Gondwana deserves a moment. This was not just a landmass. This was the landmass, a continent so enormous that if you were somehow dropped onto it, you would have no idea where you were. You might be standing on what would one day become Brazil, or the Sahara, or the Indian subcontinent, or the frozen plains of East Antarctica. The addresses hadn't been assigned yet. The whole thing was one enormous geological neighbourhood, and Antarctica was right in the middle of it. For hundreds of millions of years Gondwana held together, shifting slowly with the tectonic patience of something that has absolutely nowhere to be. Life evolved on it, spread across it, and adapted to it. And then, slowly, with all the drama of a very long goodbye, it began to break apart. And Antarctica started its long, lonely journey south. Think of Gondwana as the original group chat. Everyone was connected. Species could spread from what is now South America, into what is now Antarctica, into what is now Australia, without crossing an ocean. They just walked, or slithered, or shuffled along on whatever early mammals used for locomotion before they fully committed to legs. There were no barriers, no seas to cross, no borders to negotiate. The southern hemisphere was one continuous landmass, and life treated it accordingly, spreading and diversifying across it with the casual confidence of something that has never been told it can't go somewhere. The evidence of this ancient connectivity is written in the biology of the modern world if you know where to look. The southern beech tree, Nothofagus, grows today in southern South America, New Zealand and Australia, not because seeds cross the open ocean, they can't, but because the tree evolved when all of those places were connected, when you could have walked from one to the other without getting your feet wet. The same goes for certain groups of freshwater fish, certain families of insects, certain marsupial lineages. They are living proof that Gondwana existed. They are the biological fingerprints of a supercontinent that broke apart so long ago that no human being has ever seen it, and yet whose shape is still readable in the distribution of life across the southern hemisphere. Antarctica's position within Gondwana was not at the South Pole, at least not initially. The whole assembly shifted over time, and Antarctica's relationship with the pole changed as the supercontinent drifted and eventually fragmented. This is important because it means that for long stretches of Gondwana's history, the land that would become Antarctica was at latitudes where warmth was entirely possible. It was not always a polar continent. It became one. And that distinction between a continent that happens to be at the pole and a continent that is frozen because it happens to be at the pole is at the heart of everything that follows. By the time Gondwana was in its final stages of breakup, around 180 million years ago, Antarctica was already developing its own distinct geological identity. The connections were severing one by one, the group chat was going quiet, and the great southern continent, for the first time in its long history, a whole, was beginning to find itself alone. It did not yet know what that would mean. The forests were still there. The warmth was still there. The ice was still millions of years in the future. For now, Gondwana was simply a world in the process of becoming many worlds. And Antarctica was the piece that got left behind. Here is the part where things get genuinely unfair. There was a time, a long, lush, scientifically verified time, when Antarctica was warm, not Florida warm, not even mild English spring warm, but warm enough for forests, warm enough for rivers, warm enough for animals to live there year-round without immediately reconsidering their life choices. This period, roughly between 100 million and 34 million years ago, is known as the Greenhouse Earth era, and Antarctica was in the thick of it. Average temperatures near the coast may have reached as high as 50 to 60 degrees Fahrenheit during warmer periods. There was no permanent ice. The Southern Ocean was considerably warmer than it is today, and the continent itself, though already drifting toward the pole, was covered in something that would stop any modern geologist in their tracks: trees. To be clear about what this means, you could have stood on ancient Antarctic soil in an era that was not some bizarre cosmic exception, but simply the normal state of the planet at the time, and been comfortable. Not Arctic gear comfortable, not 4 layers and a balaclava comfortable, just comfortable. The kind of comfortable where you might roll up your sleeves. The kind of comfortable where something with fur or feathers might sit on a branch nearby and none of it would seem remarkable. That is how different the world was. That is how completely the ice has rewritten the story of this place. The Greenhouse Earth era was driven by atmospheric carbon dioxide levels that were dramatically higher than today, in some periods 3 to 8 times higher. This is not a judgment. It is a fact about the chemistry of ancient atmospheres, preserved in rock and ice, and the chemical signatures of ancient ocean sediments. The high CO2 kept global temperatures elevated, prevented permanent polar ice caps from forming, and created a world where tropical forests extended much further toward the poles than they do today. Antarctica was not a tropical rainforest. Let's not get carried away. But it was a place of genuine seasonal warmth, of rivers running freely, of soil that could grow things. Imagine the Antarctic coastline in this era. You're standing on a beach, a real beach, with sand or shingle, with waves coming in off a warmer Southern Ocean, with the smell of actual vegetation coming from behind you. There are no ice cliffs, there are no research stations, there is no ship on the horizon with a red hull and a crew of people questioning their career choices. There's just a coast, and behind it, a hinterland of dense green, and above it, a sky that is blue and unremarkable and perfect. The polar night still comes, because the Earth still tilts. In winter, Antarctica still goes dark for months. But the cold that fills that darkness is not the lethal, bone-grinding cold of today. It is a chill, or a seasonal inconvenience, the kind of cold that means the plants go dormant and the animals find somewhere sheltered, and then spring comes and everything starts again. This world lasted in various forms for tens of millions of years. Tens of millions. That is not a rounding error. That is the actual length of time that Antarctica was a living, warm, functional ecosystem. The frozen continent, you know, is younger, in geological terms, than the warm one it replaced. The ice is the newcomer. The forests were the original residents, and no one asked them if they wanted to leave. Let's talk about the forests, because the forests are where this story gets genuinely surreal. Fossilized wood, petrified tree stumps, preserved pollen from plants that haven't existed for tens of millions of years. Scientists have found all of this in Antarctica. They're poking out of rock formations and glacial debris, whispering about a world that should not, by any reasonable logic, have existed that far south. The most extraordinary discovery is the presence of ancient forests that survived the polar night, the months-long darkness that descends on the poles every winter. These were not scraggly, confused trees clinging to existence. These were dense, established forests of species related to modern conifers and deciduous trees, growing in soil, competing for light, dropping leaves, doing all the things trees do, except they were doing it at the bottom of the world, in what is now the most hostile environment on the planet. The polar night is the thing that makes this most difficult to wrap your mind around. Today, if you spend the winter at a research station in Antarctica, you go months without seeing the sun. The darkness is total, and the cold that fills it is the kind of cold that makes your breath freeze in your beard and your exposed skin start complaining within about 45 seconds. Modern Antarctic trees, there are none, obviously, would not survive this. Most plants need light. Most trees, deprived of sun for months at a stretch, would simply die. And yet the fossilized evidence shows that ancient Antarctic forests were dense and productive. So how did they do it? The answer, scientists believe, is that these were trees specifically adapted to a boom and bust photosynthetic cycle. During the long Antarctic summer, when the sun barely sets and light is available almost around the clock, these trees would have photosynthesized with extraordinary intensity, absorbing light, building sugars, storing energy in their trunks and roots with the urgency of something that knows winter is coming and is not going to be gentle about it. Then, when the polar night arrived, they would go dormant, completely dormant, shutting down, drawing on stored reserves, waiting in the dark. It is the botanical equivalent of going into a very deep sleep for several months and hoping your alarm works. Apparently, for millions of years, it did. The fossilized wood found in Antarctica tells this story in its growth rings, the same rings that tell us how old a tree is and what its growing seasons were like. Antarctic fossil wood shows extremely compressed growth rings, meaning very rapid growth followed by very little growth, over and over, season after season. These trees were sprinting through their summers and sitting very still through their winters, for millions of years, in a place that is now a sheet of ice 2 kilometers thick. You can hold a piece of Antarctic fossil wood in your hand, and scientists have. Some of it is remarkably well preserved, the cellular structure still visible under a microscope. You're holding a piece of a tree that grew at the South Pole when dinosaurs were alive. A tree that photosynthesized ancient air. A tree whose roots once reached into warm Antarctic soil that is now buried under a continent's worth of ice. It is the kind of object that makes you want to sit down quietly for a while and think about what time actually means. The forests are gone, the soil they grew in is gone, the animals that lived among them are gone, but the wood remains, and they're scattered across the rock exposures of Antarctica like calling cards from a world that the ice tried very hard to erase entirely, and almost succeeded. Almost. Now here is a sentence that sounds like it was generated by a malfunctioning history app, but is completely, documentably true. Dinosaurs lived in Antarctica, not wandered past, not briefly visited, lived there. Fossils of multiple dinosaur species have been recovered from Antarctic rock, and the implications are deeply strange to sit with. Among the species discovered is Cryolophosaurus, a predatory dinosaur with a peculiar bony crest on its head that paleontologists have described, with great affection, as looking like a pompadour. It lived during the early Jurassic period, roughly 190 million years ago, when Antarctica was still attached to other land masses and considerably warmer than today. You would have been able to walk from what is now Antarctica into what is now South America, and apparently if you had, you might have come face to face with something that had excellent hair and very bad intentions. Cryolophosaurus was not tiny. It was roughly 6 meters long, walked on 2 legs, had small forelimbs, and possessed the bony head crest that has made it something of a celebrity among Antarctic paleontologists. Nobody's entirely sure what the crest was for. It may have been for display, attracting mates, intimidating rivals, the dinosaur equivalent of a very dramatic hat. What is certain is that Cryolophosaurus was a predator, a mid-sized meat-eater operating in a world that was already deeply strange by modern standards, and presumably stranger still if you were the thing it was chasing. But Cryolophosaurus was not alone. Other dinosaur fossils have also been recovered from Antarctica, including Glacialisaurus, a large plant-eating dinosaur from the same time period, and various other fragmentary remains that suggest a functioning populated ecosystem on a continent that most people today associate exclusively with penguins and blizzards. There were also early mammal-like reptiles, the therapsids, whose descendants would eventually give rise to mammals, including, improbably, us. The Antarctic Jurassic was not a quiet or uneventful place. It was a real working world, with predators and prey, with competition and survival, with the whole noisy, violent, complex business of life getting on with itself. The polar night would still have been a factor, even in the warm Jurassic. These dinosaurs would have experienced months of darkness. How they managed this is not entirely understood. Some paleontologists suggest that the large plant-eaters may have migrated toward the coast during winter, where temperatures were milder. Others suggest that polar dinosaurs may have simply endured the darkness, slowing their metabolism in the way that some large modern animals do during winter. There is evidence from other polar dinosaur sites, notably in Alaska, that suggests at least some species lived in high latitudes year-round. Whatever they did, they managed. For millions of years they managed. The image of a Jurassic Antarctic forest populated by dinosaurs is one of the most genuinely astonishing things that science has established about this planet. Not because it was unimaginable. Science fiction has been putting dinosaurs in strange places for over a century, but because it is real. It happened, on this Earth, on the land that is now buried under the ice at the bottom of the world. Somewhere under 2 kilometers of Antarctic ice, there is a rock with a dinosaur footprint in it. We just haven't found it yet. Before the continent froze, the seas around it were a different world entirely. The Southern Ocean as we know it, wild, ice-choked, ferociously cold, the kind of ocean that looks at sailors and sighs, did not yet exist in that form. In the age of the greenhouse Earth, the waters surrounding Antarctica were warm enough to support an extraordinary diversity of marine life. Ancient marine reptiles slid through these seas, giant ammonites, those magnificent spiral-shelled creatures that look like something designed by an architect who really loved geometry, drifted in vast numbers. Primitive whales and their ancestors made their first tentative appearances in southern waters. The coastline itself was nothing like the sheer ice cliffs we see today. It was a living, breathing shoreline with beaches, estuaries and shallow coastal waters teeming with life. Close your eyes and rebuild this world from the water up. The ocean here, in the Cretaceous and early Paleogene, is warm enough to be hospitable. Not bathwater warm, not Caribbean warm, but something closer to a cool, temperate sea. The kind of ocean you might swim in on a brisk but determined summer holiday. The water is a deep, clear blue-green. The light penetrates far beneath the surface, supporting the photosynthetic plankton that forms the base of the entire marine food web, and from that base life has built something extraordinary. Below the surface, the ancient Southern Ocean is dense with creatures that have no modern equivalents. The ammonites are everywhere. Some are small, a few centimetres across, others are enormous, reaching diameters of 1 metre or more. Their coiled shells, chambered and precisely engineered, allowed them to control their buoyancy with extraordinary precision. They have been extinct for 66 million years, victims of the same mass extinction event that took the non-avian dinosaurs, and yet their fossilised shells are found on every continent, including Antarctica. They were the ocean's background character, always present, always abundant, a constant in the marine world for hundreds of millions of years, and then, very suddenly, not. Marine reptiles patrolled these ancient southern waters for much of the Mesozoic era. Plesiosaurs, those long-necked, paddle-limbed creatures that have fueled 150 years of Loch Ness Monster speculation, were real animals that genuinely swam in ancient Antarctic seas. Fossil plesiosaur bones have been found on Vega Island, off the Antarctic peninsula, including the remains of an Elasmosaurus-type plesiosaur, a creature with a neck so long it made up roughly half its total body length. It glided through warm, ancient waters, hunting fish and other marine prey, in a sea that would one day become one of the most ferocious and least hospitable bodies of water on Earth. The transition from this warm, life-rich ancient ocean to the modern Southern Ocean is one of the most dramatic transformations in the history of marine ecology. When the Antarctic circumpolar current established itself and the waters cooled, the entire ecosystem of the southern seas was restructured. Cold water species moved in, warm water species retreated or went extinct. The diversity of the ancient ocean, all those marine reptiles, all those ammonites, all those warm water mollusks and corals, was replaced by a leaner, colder, but still remarkably productive ecosystem built around krill, cold-adapted fish, seals, and eventually penguins. The modern Southern Ocean is not empty. It is one of the most productive marine ecosystems on Earth. But it's a very different ocean from the one that once lapped at warm Antarctic beaches, this under a sky that had never heard of ice. What swam there is gone. The water remains. Let's talk about the breakup. Not the emotional kind, though there is a certain sadness to it, but the geological kind, which took approximately 180 million years and involved a truly staggering amount of real estate. Gondwana did not split apart all at once. It did it slowly, in stages, like someone methodically tearing a very large piece of paper. Africa peeled away first, around 180 million years ago. Then South America, then India, which drifted north with unusual speed and eventually slammed into Asia hard enough to create the Himalayas, a fact that remains one of geology's most dramatic plot twists. Australia and Antarctica stayed connected for longer than anyone else, drifting together like old friends reluctant to part ways, until finally, around 35 million years ago, Australia broke north and Antarctica was left alone at the bottom of the world. And that is when everything changed. Picture the globe in the early Jurassic period, 180 million years ago. From above, from space, you can see the enormous dark mass of Gondwana sitting mostly in the southern hemisphere, vast and intact. The Tethys Sea laps at its northern margin. The Proto-Atlantic barely exists. It is a narrow rift, a crack in the Earth's crust, barely worthy of the name ocean yet. And below all of it, connected and whole, is the land that will become 6 separate continents. The mechanism of the breakup is plate tectonics, the slow, relentless movement of the rigid plates that make up the Earth's outer shell are driven by the heat of the planet's interior. Where plates pull apart, new seafloor forms as magma rises to fill the gap. Where plates collide, mountains are built or one plate is forced beneath the other. It is a system of almost incomprehensible scale, operating on time scales that make human history seem like a rounding error. And it is the reason that Antarctica is where it is, doing what it does, covered in exactly the amount of ice it is covered in. Africa's departure opened the Indian Ocean on one side and widened the South Atlantic on the other. South America eventually followed, and the South Atlantic became a real ocean, wide and permanent. India moved north at what is, by tectonic standards, a reckless speed, perhaps 15 to 20 centimetres per year at its fastest, and crossing from its original position off the coast of Antarctica to its eventual collision with Asia in a journey that took roughly 50 million years. The Himalayas, the tallest mountains on Earth, are the direct result of that collision. They are, in the most literal possible sense, the scar left by a piece of Antarctica's ancient family smashing into something at geological speed. Australia and Antarctica lingered. Of all the Gondwana fragments, they were the last to fully separate. For tens of millions of years after Africa and South America had gone their separate ways, Australia and Antarctica remained attached along their southern margins, sharing coastline, sharing species, sharing the slow drift southward that would eventually doom Antarctica to the ice. When Australia finally broke free, around 35 to 33 million years ago, and began its northward drift toward its current position, it was the final act of the Gondwana breakup. The last connection was severed. Antarctica was alone. No other landmass was coming to keep it company. No ocean current from the tropics could now wrap around and warm it. The cold had a clear path, and it took it. Here is the moment everything goes wrong or right, depending on your feelings about penguins. When South America finally separated from Antarctica, it opened up a deep oceanic channel between the two continents, the Drake Passage. This might sound like a minor geographical detail, the kind of thing only a cartographer would get excited about. But the opening of the Drake Passage is one of the most consequential events in the last 50 million years of Earth's climate history. Before the passage opened, ocean currents could not fully circulate around Antarctica. Warm water from the tropics still made its way south, tempering the climate. But once the Drake Passage opened wide enough, a new and ferocious current formed, the Antarctic Circumpolar Current, the strongest ocean current on Earth. It wrapped around Antarctica like a belt, cutting it off from the warmer waters of the rest of the world, and Antarctica slowly, inexorably began to freeze. The Drake Passage today is one of the most feared stretches of water on the planet. It connects the South Atlantic and the South Pacific between the southern tip of South America and the northern tip of the Antarctic Peninsula. It is roughly 800 kilometers wide, and through it, the entire volume of the world's oceans essentially circulates, all of it funneled through this one relatively narrow channel, driven by the relentless westerly winds that blow unobstructed around the Southern Ocean. Waves in the Drake Passage can reach 20 meters in height. Ships that cross it routinely describe it as the most violent water they have ever encountered. Sailors have a name for the latitudes just north of it: the Roaring Forties, the Furious 50s, and the Screaming 60s. But in the Eocene epoch, around 35 to 32 million years ago, the Drake Passage did not yet exist as a deep navigable channel. South America and Antarctica were still close enough, connected by a chain of shallow seafloor that water could not freely flow through. The currents of the southern hemisphere were forced to turn north before they could complete a circuit around Antarctica. This deflection allowed warm tropical water to reach the Southern Ocean and moderate Antarctica's climate. It was, in effect, a heating system for the bottom of the world, imperfect and indirect, but real. When the Drake Passage deepened sufficiently to allow the circumpolar current to establish itself, the heating system was switched off. The warm water that had been reaching Antarctica was now deflected, held away from the continent by the new current flowing around it. The Southern Ocean began to cool. the temperature gradient between the Antarctic coast and the tropics steepened sharply. Winds intensified. The thermal isolation of Antarctica was for the first time nearly complete. The oceanographers who study the Antarctic circumpolar current today describe it with a mixture of awe and respect. It carries roughly 135 million cubic meters of water per second. That is more than all the world's rivers combined, flowing through one channel in one direction, endlessly. It is the engine of global ocean circulation. It drives the deep water formation that distributes nutrients and oxygen throughout the world's oceans. It is, in many ways, one of the most important features on the planet. It is also, from Antarctica's perspective, the thing that sealed its fate. The most powerful ocean current on Earth formed, wrapped around the most isolated continent on Earth, and turned it into the coldest place on Earth. As climate mechanisms go, that is an impressively complete job. Yeah, the freezing of Antarctica was not a sudden catastrophe. It didn't happen overnight, or even over a human lifetime, or over 1,000 human lifetimes. It was a process measured in millions of years, and it was, by the standards of geological history, relentless. Around 34 million years ago, during a period geologists call the Eocene-Oligocene transition, global temperatures dropped sharply. Carbon dioxide levels in the atmosphere fell. The Antarctic circumpolar current was now in full force, strangling the continent's access to warmth. Ice began to accumulate in the highest elevations first, in the mountains of East Antarctica, where the cold collected like water in a bowl. Each winter, a little more snow fell than melted the following summer. Year by year, century by century, the ice sheets grew, the forests retreated. The rivers slowed, then froze. The coastline shrank under advancing glaciers. The ancient world was being buried layer by layer in the most patient act of erasure in Earth's history. The mechanism of glaciation is, at its core, beautifully simple. Snow falls. If the temperature never warms enough to melt all of it before the next winter comes, some of it stays. The next winter, more snow falls on top. The layer from last year is compressed. Over time, compressed snow becomes firn, a dense intermediate form between snow and ice. Over more time, firn becomes glacial ice, a different material entirely, deep blue-white, virtually airless, so dense and heavy that it flows under its own weight like an extremely slow, extremely cold river, and as the ice builds up, it starts to do something important. It reflects sunlight. The technical term is albedo. A dark surface absorbs heat. A white surface reflects it. As Antarctica's ice sheets grew, they reflected more and more of the solar energy hitting the continent back into space, cooling the surface further, allowing even more ice to accumulate. It was a feedback loop with no off switch. The forest did not die all at once. In the early stages of the glaciation, when ice was building in the high interior while the coast remained relatively mild, there would have been a period of strange coexistence. Ice on the mountain tops, forests in the valleys, coastal wetlands still alive with birds and insects, even as the world behind them slowly turned white. If you had been there, if some impossible time-travelling version of you had stood on an Antarctic beach 30 million years ago, you might have seen snow on the peaks behind you and still felt a cool but livable breeze on your face. You might have thought, this is fine, this is just weather. But it wasn't weather. It was the end of a world, and it was moving toward you at a speed you would never have been able to detect in a human lifetime. The ice advanced at the pace of centimetres per year, of meters per century, of kilometres per millennium. On the scale of a human life, it was invisible. On the scale of geological time, it was a landslide. The Eocene-Oligocene transition is one of the most significant climate events in the last 100 million years of Earth's history. In a relatively short geological window, perhaps a few 100,000 years, the planet lost much of its greenhouse warmth. Ice sheets formed at both poles for the first time in millions of years, and global sea levels dropped by dozens of meters as vast quantities of water were locked up in glacial ice. The green continent went white, and it has stayed white ever since. It is the longest cold snap in recent geological history, and there is no sign it is going to break any time soon. The forest never came back. As the ice advanced, the forest didn't simply disappear overnight. They retreated. Species that had thrived in the warm southern latitudes for tens of millions of years found themselves caught in a slow-motion catastrophe, edging northward toward the coasts as their habitat contracted, then running out of coastline and then running out of continent. The fossil record from this period is a story told in preserved pollen. In the stumps of trees that died in place and were slowly entombed in ice and sediment, in the chemical signatures of ancient soil layers that tell scientists exactly when the last organic life vanished from a given location. These were not small, scrubby plants. Some of the last Antarctic forests were composed of species related to the southern beech, Nothofagus, a genus that still survives today in the southernmost tips of South America and New Zealand, living descendants of trees that once covered the Antarctic continent, now marooned on the other side of the world, their ancestral home buried under 2 miles of ice. The southern beech is a quietly extraordinary tree. It is not the most dramatic-looking tree in the world. It is not towering or ancient-looking in the way of a redwood or a baobab. It grows in cool, damp climates. It produces small, serrated leaves and forms dense forests that are often mossy and atmospheric and slightly melancholy. And it grows today in Patagonia and in New Zealand, 2 places that, to a modern traveller, seem to have nothing in common at all, except geology, except deep time, except the fact that both are fragments of Gondwana, and the southern beech is a living relic of a world that existed before those fragments separated. The last Antarctic Nothofagus forest died somewhere around 30 to 34 million years ago, as the ice finally advanced far enough and the climate cooled past the point where even a cold-adapted, deciduous polar night surviving tree could hold on. The stumps of some of these trees preserved in Antarctic sedimentary rock are still there. Scientists have photographed them. Some are still in their original growth position, standing in the rock just as they stood in the ancient soil, before the cold came for them. A tree stump in Antarctica is one of the most melancholy objects in science. Not because it is sad in any human sense, but because of what it represents. The very last moment of life in a place that has been lifeless ever since. When those last trees died, Antarctica went silent in a way that it had never been silent before. The insects that had lived among them disappeared. The birds that had nested in them disappeared. The small mammals that had sheltered beneath them disappeared. Not instantly. Life is stubborn, and the margins near the coast may have held on for some time after the interior went cold, but eventually completely. The continent was emptied, not by a single catastrophe, not by a meteor or a flood or a volcanic eruption, but by the slow, inexorable, grinding cold of a glaciation that simply never stopped. What replaced the forests was ice. And under the ice, in the cold and the dark and the pressure, the ancient world was compressed. The logs became coal, the soils became rock, the rivers became fjords, filled in with glacial sediment. The entire living landscape was converted over millions of years into the geological record, still there, still legible to those who know how to read it, but no longer alive, no longer warm, no longer green. Somewhere in Antarctica, under kilometres of ice, there is the ghost of a forest. The roots are still in the soil is still there, frozen and compressed, waiting. It has been waiting for 30 million years. It is very patient. The forests were not empty. That is the thing that is hardest to wrap your mind around. Standing in front of photographs of Antarctica today, all that white silence, all that absence of life above the ice. Because for tens of millions of years, Antarctica was full. Not New York City full, not Amazon rainforest full, but full in the way that any warm, vegetated land is full. With insects, birds, small mammals, large reptiles, and the slow, constant hum of ecological activity. Fossilized remains have given scientists remarkable glimpses of this lost world. There were marsupials, ancestors of the pouched mammals that today live in Australia and South America, who crossed Antarctica when it was still connected to both. There were flightless birds, early relatives of the ratites plodding through undergrowth. There were giant insects, primitive mammals, and a whole caste of creatures that vanished so completely that their very existence had to be inferred from bones pressed into rock. Let's start with the marsupials, because the marsupials are doing something genuinely surprising. Today, if you think of marsupials, you probably think of Australia, kangaroos, wallabies. The wombat, which is essentially a marsupial that gave up halfway through becoming something else and decided it was fine with that. But marsupials did not originate in Australia. Their oldest fossil relatives are found in North America, and the group spread southward through South America and across Antarctica into Australia back when all those places were still connected by the Gondwana land bridge. Antarctica was not just a place marsupials passed through on their way to Australia. It was a place where they lived. So for millions of years, in forests that were warm enough and productive enough to support a functioning mammalian fauna. Fossil fragments from Seymour Island, off the Antarctic Peninsula, have revealed small marsupials and other early mammals that lived in Antarctica during the Eocene epoch, roughly 40 to 50 million years ago. These were not giants. They were small, probably nocturnal, probably living in the underbrush in the way that small mammals everywhere tend to live, cautiously, quietly, very alert to things bigger than themselves, but they were there. On a continent that is now defined by the almost total absence of land mammals, there were once small furry creatures going about their small furry business in the Antarctic undergrowth. The birds of ancient Antarctica are also worth pausing on. Among them, and this is a discovery that delighted paleontologists enormously, very early penguins. The oldest known penguin fossils come from New Zealand and Antarctica, and they are startlingly large. Kumimanu bisei, one of the largest known fossil penguins, stood roughly 1.6 metres tall and weighed somewhere around 100 kilograms. That is a bird approximately the size of a grown adult human, waddling around ancient Antarctic beaches, presumably very pleased with itself. The early penguins lived in the warm Antarctic oceans of the Eocene, long before the continent froze, fishing in warm coastal waters, nesting on beaches that no longer exist. They are, in a very meaningful sense, the oldest living connection between modern Antarctica and its ancient warm past. Their descendants are still there, on the ice. Cease having adapted to a world their ancestors would not have recognised. There were also giant insects in the ancient Antarctic world, not science fiction giant, but large enough to notice. The warm, oxygen-rich air of the greenhouse Earth supported arthropods of considerable size, and Antarctica's forests would have buzzed and clicked and hummed with them. Beetles, flies, moths, the kind of insect life that turns a forest from a collection of trees into an ecosystem. When the cold came and the forest died, all of this went with them. The marsupials, the birds, the insects, the small mammals in the undergrowth, an entire community of life, assembled over millions of years, erased by the ice. It did not leave quietly. It just left no forwarding address. Around 34 million years ago, the East Antarctic ice sheet began to form. Then, and nothing would ever be the same again. This was not a gradual dusting of frost. This was the beginning of the largest accumulation of ice on the planet, a mass of frozen water so enormous that if it melted entirely, global sea levels would rise by roughly 53 to 60 meters. The whole world's coastlines would vanish. Cities that currently have ocean views would be ocean floors. The ice sheet grew slowly at first, covering the high interior plateaus, then descending toward the coasts, grinding over everything in its path. What had been soil became permafrost. What had been riverbeds became valleys carved by glaciers. What had been a living landscape of trees and animals became, over millions of years, the most sterile, most extreme, most deeply hostile environment on the surface of the Earth. And it has remained that way, more or less, ever since. The East Antarctic ice sheet is old. Not old in the way of a medieval building or an ancient city, old in the way of mountains and oceans. The ice at its deepest layers is over 1 million years old, compressed from snow that fell on a world without a single human being in it, before our genus had appeared anywhere on Earth. You could drill down through that ice and pull out a core sample from 800,000 years ago, and hold in your hands air that has not been in contact with the atmosphere since before we existed. The ice is not just frozen water, it is a time machine, and it has been running, without interruption, for 34 million years. The formation of the ice sheet had immediate and dramatic effects on the rest of the planet. As ice accumulated on Antarctica, sea levels around the world dropped because water that had previously been in the ocean was now locked in the ice. Enormous areas of shallow continental shelf were exposed as dry land. The global climate cooled further, driven by the increased albedo of the new ice sheet reflecting solar energy away from Earth. Ocean circulation patterns shifted as cold, dense water began to form around Antarctica and sink to the deep ocean floor, spreading outward in all directions and fundamentally reorganizing the way heat moves around the planet. The grinding of the ice over the Antarctic bedrock was, and continues to be, one of the most powerful erosive forces on Earth. Glaciers do not just sit on landscapes, they reshape them. They carve valleys into U-shapes, deepen fjords, grind mountains into smooth-sided nunataks, and the isolated rocky peaks that poke above the surface of the ice sheet like survivors of a frozen flood. The ancient river valleys of Antarctica were deepened and widened by glacial erosion into the dramatic troughs that now lie beneath the ice, some of them descending well below sea level. The landscape that exists beneath the Antarctic ice sheet is not the same landscape that existed before the ice arrived. The ice has been remodeling for 34 million years, and it has done a thorough job. Today, the East Antarctic ice sheet contains roughly 26.5 million cubic kilometres of ice. If you could somehow stack that ice in a column 1 kilometre square, it would reach from the Earth's surface to the Moon and considerably beyond. It is, by any reasonable measure, an incomprehensible quantity of frozen water. Sitting on a continent at the bottom of the world, holding an entire ancient world underneath it like a hand pressed flat on a table, preventing anything from getting up. The freezer got switched on 34 million years ago. Nobody has found the thermostat since. Here is where the ice stops being a villain and starts being something genuinely extraordinary. Because the same ice that buried the ancient world of Antarctica also preserved it. Not perfectly, not in the way of amber or tar pits, but in ways that have given scientists priceless information about the history of the Earth's climate. Deep ice cores drilled from the Antarctic ice sheet contain trapped air bubbles that are, in effect, samples of the Earth's ancient atmosphere. When you pull out a core from deep enough in the ice, You're holding air that was breathed by creatures that no longer exist, from a time before humans had appeared anywhere on Earth. These cores have allowed scientists to reconstruct atmospheric carbon dioxide levels going back hundreds of thousands of years, revealing patterns of warming and cooling that are now central to our understanding of how the Earth's climate system works. The drilling of deep ice cores is one of the most painstaking and technically demanding operations in all of science. It takes place at some of the most remote and brutal locations on Earth, stations like Vostok and Dome Sea in East Antarctica, where the temperatures routinely drop below minus 40 degrees Celsius even in summer, and the altitude causes mild hypoxia in anyone not acclimatized to it. The drilling itself is slow, deliberate and deeply careful. Because an ice core is fragile, crack it and you lose the air bubbles it contains, warm it and the ancient air escapes. The entire point of the exercise is to bring a cylinder of ancient ice to the surface, intact, so that what is trapped inside it can be measured with scientific precision. What comes out of a deep ice core is a record of the Earth's past that no other archive can match. The air bubbles preserve the exact composition of the ancient atmosphere, the concentrations of carbon dioxide, methane and other greenhouse gases at the time the ice formed. The ice itself, analysed chemically, reveals the temperature of the air above Antarctica when the snow fell. Dust particles trapped in the ice tell stories about ancient wind patterns and volcanic eruptions. Pollen grains trapped in the ice whisper about vegetation that grew near the margins of the continent when certain layers were laid down. The oldest ice core ever successfully drilled, recovered from a site called Little Dome Sea by a joint European-Australian team, extends back approximately 1.2 million years. Scientists are currently working toward drilling ice that may be 2 million years old, a period that would take the record back before the current pattern of ice age cycles and into an earlier, less well-understood climate regime. The goal is not merely academic. Understanding how the climate system behaved under different atmospheric conditions in the deep past is one of the most important tools we have for projecting how it will behave in the future. But there is something else preserved in Antarctic ice and rock that is even more elemental than atmospheric chemistry. Preserved in the ancient sedimentary rocks of Antarctica, the ones that predate the ice sheet, the ones that poke through the ice at the edges of the continent, are the physical remains of the world that existed before the freeze, fossil pollen, fossilized wood, the bones of ancient creatures, the imprints of leaves. These are not merely scientific data. They are messages written by a world that no longer exists, addressed to whoever was patient and determined enough to dig them out. The ice buried everything, and in burying it, it kept it. Cold, dark, compressed, and perfectly silent. A library no one knew existed, written in wood and bone and ancient air. Scientists have been reading it for decades. They are nowhere near finished. Here is something that sounds impossible, but is thoroughly, rigorously documented. Antarctica has rivers and lakes under the ice, right now. Buried beneath kilometres of glacial ice, warmed from below by geothermal heat from the Earth's interior, there is an entire hidden hydrological system, a network of subglacial lakes connected by rivers and channels, flowing unseen in the total darkness beneath the ice sheet. The most famous of these is Lake Vostok, a subglacial lake roughly the size of Lake Ontario, buried under nearly 4 kilometres of ice. It has been isolated from the surface for somewhere between 15 and 25 million years. The water in it is ancient. The organisms that may live in it, and scientists believe something does live in it, have been cut off from the rest of life on Earth for longer than our genus has existed. It is, in every meaningful sense, an alien world, and it is located on our own planet. Lake Vostok was not discovered by drilling down and finding it. It was discovered by radar. In the 1970s and 80s, airborne radar surveys of the Antarctic ice sheet began to reveal something unexpected. a region beneath the ice at the Russian Vostok station, where the radar signal was reflecting off a perfectly flat surface at a consistent depth. Flat surfaces beneath ice sheets mean water. Specifically, they mean liquid water, which forms a mirror-like boundary with the ice above it. The flat reflective anomaly beneath Vostok Station turned out to be one of the largest subglacial lakes in the world, thus roughly 250 kilometres long and 50 kilometres wide, sitting at a depth of nearly 4 kilometres under the ice. The water in Lake Vostok is liquid despite being buried under enormous pressure and surrounded by ice because of two factors. The pressure of the overlying ice lowers the melting point of ice slightly, meaning it melts at the ice-water interface and keeps the lake supplied with liquid water. And below the lake, geothermal heat from the Earth's interior provides a steady, gentle warmth. Not dramatic, not volcanic, just the slow, consistent warmth of a planet that has a molten core and leaks heat through its crust. The combination keeps Lake Vostok in a stable, liquid state that has persisted for millions of years. Scientists drilled through to the lake in 2012, after decades of negotiation about whether and how to do it without contaminating this pristine ancient water system with modern microbes. The samples they retrieved from the ice just above the lake surface showed evidence of microbial life, bacteria and other microorganisms adapted to the extreme cold, darkness, and pressure of the subglacial environment. Whether the lake itself hosts life remains a subject of active research. What is certain is that if life exists in Lake Vostok, it has been evolving in complete isolation, in total darkness, under crushing pressure, for somewhere between 15 and 25 million years. Lake Vostok is not alone. Scientists have now identified more than 400 subglacial lakes beneath the Antarctic ice sheet, connected in many cases by subglacial rivers that drain from one to another, flowing through channels carved in the bedrock by ancient meltwater. The whole system moves slowly beneath the ice, a hidden circulatory system in a continent that looks, from the surface, like the definition of still. This hidden world, dark, cold, pressurized, ancient, potentially alive, is one of the most extraordinary environments on Earth, and most people will never know it exists because it is buried under 2 miles of ice at the bottom of the world, quietly doing whatever it has been doing for 20 million years. That is a very long time to be left alone with your thoughts. Before the ice, Antarctica had coastlines, real ones. Not the sheer cliffs of ice that carve into the Southern Ocean today, but actual beaches, estuaries, bays and headlands shaped by wind and water over millions of years. Radar surveys and satellite data have now given scientists a detailed picture of what lies beneath the ice, the true topography of the Antarctic continent, the shape of the land as it existed before it was buried. And what they have found is not a flat, featureless plain. Antarctica, stripped of its ice, would reveal a remarkably complex landscape, mountain ranges, deep basins, river valleys, and in places low-lying coastal areas that were once, in the warm epochs, likely to have been tidal flats or shallow wetlands. One of the most striking features is the Gamburtsev mountain range, a chain of peaks buried entirely under the East Antarctic ice sheet, roughly the size of the European Alps, completely invisible from the surface, undiscovered until the mid-20th century. Imagine the ancient Antarctic coastline in its prime, not the far southern prime of the deep Mesozoic, but the more recent warm period of the Eocene, perhaps 40 to 45 million years ago. The ice is not yet there. The land behind you slopes gently down from ranges visible in the distance to a coastal plain that spreads out toward the sea. There are rivers. You can hear them if you listen. The low, constant sound of moving water over rock, the thing that more than almost anything else signals that a landscape is alive. The rivers run from the highlands toward the coast, cutting valleys, depositing sediment in deltas and estuaries, carving the kind of slow, patient landscape that rivers make everywhere on Earth when given enough time. The beaches of ancient Antarctica would have been shaped by the same forces that shape beaches everywhere: wave action, tidal rhythm, longshore drift carrying sediment along the coast and depositing it in spits and bars. There would have been tidal flats at river mouths, covered at high tide and exposed at low tide, rich with the burrowing invertebrates that colonize such places. There would have been shallow coastal waters, warmed by the summer sun, supporting beds of kelp and the fish and marine mammals that depend on them. It would have looked, in a general way, like the coast of southern Chile or New Zealand today: cool, green-fringed, rainy, alive. The Gambutsev Mountains deserve a special mention because they are one of the great hidden surprises of Antarctic geology. Their existence was first suspected in the late 1950s during the International Geophysical Year, is when Soviet scientists conducting seismic surveys noticed anomalies in the ice that suggested a mountain range beneath. Subsequent radar surveys have confirmed them in extraordinary detail: peaks rising to over 3,000 metres, valleys carved by ancient glaciers, a complete mountain range the size of the Alps hidden beneath the East Antarctic ice sheet so completely that no human being has ever seen them, or is likely to. You could fly over them and see nothing but flat white ice. The mountains are there, under your feet, in the dark. The ancient coastlines of Antarctica are also hidden. They lie under the ice, under the glacial sediment, under millions of years of geological overwriting. But they were real. Ships sailed along them, in imagination at least, in the warm world that preceded the ice. Tides rose and fell against them. Seabirds nested on their cliffs. Fish swam in the estuaries at their feet. Now the only coastline Antarctica has is ice, and the only thing lapping at it is a sea that has not been warm in 30 million years. Antarctica is not just a piece of geography. It is, quite literally, one of the engines of Earth's climate system, and understanding its past is one of the most important things climate scientists can do. The cold water produced around Antarctica sinks to the ocean floor and spreads throughout the world's ocean basins, driving the thermohaline circulation, the vast, slow conveyor belt of ocean currents that regulates temperatures across the entire planet. Without Antarctica's ice, the circulation would change. Without the circulation, the distribution of heat around the Earth would be dramatically different. Europe would be colder. The tropics would be warmer. Monsoons might shift. Agricultural systems built over thousands of years of relatively stable climate would be thrown into upheaval. The ancient, frozen continent at the bottom of the world is, in a very real sense, the thermostat for the rest of us. The thermohaline circulation, sometimes called the ocean conveyor belt, which is a helpful if slightly undignified way to describe one of the most powerful forces on the planet, works like this. Around Antarctica, seawater is chilled by contact with the cold atmosphere and by the formation of sea ice. When sea ice forms, it leaves salt behind in the remaining water, making that water denser. Dense, cold, salty water sinks. It sinks all the way to the ocean floor thousands of meters down, and then it spreads northward along the bottom of the Atlantic, Pacific, and Indian Oceans, slowly moving toward the equator and beyond. As it goes, it is gradually warmed by geothermal heat and by mixing with shallower water, eventually rising back to the surface somewhere in the tropics or North Atlantic. There, it is warmed further by the sun, and the surface current carries it back toward the poles, where it cools and sinks again. The whole cycle takes roughly 1,000 years for a single parcel of water to complete. This matters in ways that are immediately practical. The warm surface current that flows toward northern Europe, the North Atlantic current, which is the northern extension of the Gulf Stream, is the reason that London has mild winters while Labrador at the same latitude does not. It is the reason that Northern Europe is habitable agricultural land rather than a landscape of permafrost. That current exists because of the sinking of cold, dense water at the poles, and the cold, dense water at the South Pole is cold and dense because Antarctica is covered in ice and surrounded by sea ice that forms every winter. Take away the Antarctic ice and the whole engine changes. The conveyor slows, the heat redistribution shifts, and the consequences ripple outward to every corner of the world. Antarctica's role as a climate engine is not something that was understood for most of human history. For the vast majority of our existence as a species, Antarctica was simply a rumour, a suspected southern landmass that existed somewhere beyond the reach of any ship. Ancient Greek philosophers theorized about a southern continent for reasons of geometric symmetry. If there was land in the north, they reasoned, there must be an equivalent mass in the south to balance it. They were right for the wrong reasons. But neither they nor anyone who came after them, until the last century or two, had any idea that the frozen continent at the bottom of the world was quietly regulating the temperature of the entire planet. It does not ask for credit. It does not make announcements. It just sits there at the bottom of the world, cold and white and enormous, running the thermostat, keeping the conveyor moving, quietly ensuring that the rest of the planet's climate remains within the range of conditions that human civilization was built to inhabit. It has been doing this without complaint for 34 million years. You are welcome. When the ancient world of Antarctica froze and died, evolution did something remarkable. It adapted. Thus, the descendants of creatures who once lived in Antarctic forests or swam in warmer Antarctic seas did not simply vanish. Many of them survived by moving north, following warmth as the ice advanced, and over millions of years they evolved into new forms suited to new environments. And some, against all reasonable expectations, evolved to live in the cold. The penguin is perhaps the most spectacular example. The earliest penguins evolved from flying seabirds, and by the time Antarctica began to freeze, their lineage was already ancient. As the continent cooled, penguins evolved to exploit the new reality. They traded flight for hydrodynamic efficiency, becoming the most perfectly adapted marine hunters in the Southern Ocean. They did not survive in spite of the ice. They evolved to need it. Yet the evolutionary history of penguins is one of the more satisfying stories in paleontology, partly because it is a story of extraordinary success achieved through what looks, from the outside, like a series of increasingly extreme commitments. At some point tens of millions of years ago, an ancestor of the modern penguin, a flying seabird, probably something like a modern diving petrel, began spending more and more time in the water. Its wings, already useful for underwater propulsion, became more efficient as flippers over generations. Its body became more streamlined. Its bones, which in flying birds are hollow to reduce weight, became denser, acting as ballast to help it dive deeper. It gave up the sky in exchange for the ocean. As trades go, it turned out to be an excellent one. The giant penguins of the Eocene, like Kumimanu besi, which stood taller than many adult humans, lived in waters that were still relatively warm by modern standards. As the Southern Ocean cooled over millions of years, the penguins that survived were those best adapted to cold. Their insulating layer of densely packed waterproof feathers became more efficient. Their metabolisms adapted to extracting maximum energy from the cold water fish and krill that flourished in the new Southern Ocean ecosystem. The emperor penguin, the largest modern penguin, has taken this cold adaptation to its logical extreme. It breeds in the Antarctic winter, in temperatures that drop to minus 60 degrees Celsius, incubating its eggs on its feet in the darkness of the polar night, because the timing means that chicks will hatch in spring when food is becoming more available. So, this is either a masterpiece of evolutionary strategy or evidence that evolution sometimes runs out of easy options and just commits to the difficult one. The Antarctic fur seal, the Weddell seal, the leopard seal, the orca, all of these creatures are, in their different ways, inheritors of the cold world that replaced the warm one. They are not the descendants of the creatures that lived in ancient Antarctic forests. They are the descendants of creatures that moved south as the ice stabilized and found in the cold Southern Ocean a niche of extraordinary productivity. The Antarctic krill, Euphausia superba, a small shrimp-like crustacean that exists in swarms so dense they can be seen from space, underpins the entire modern Antarctic food web. Everything depends on krill, and krill depends on the sea ice, as using the algae that grows on its underside as its primary food source in winter. The ice is not just a backdrop, it is infrastructure. The warm world of ancient Antarctica produced extraordinary life. So did the cold world that replaced it. Evolution does not grieve, it gets to work. The ice came, new things moved in, and the bottom of the world, despite everything, stayed alive. Every fossil found in Antarctica is a message from a world that should not exist, because you do not find fossils in places that have always been frozen and barren. Fossils require life, and the very presence of fossil material in the Antarctic rock, plant matter, bones, shells, pollen, is direct, physical proof that this place was once alive. The work of finding those fossils is extraordinarily difficult. Antarctica is not a place where you casually walk the riverbank and spot a bone. Scientists must drill, dig, and search through wind-blasted exposures of ancient rock in conditions that would be considered extreme anywhere else on Earth. And yet, over the course of a century of Antarctic research, the finds have accumulated into something remarkable. A picture of an entire ancient ecosystem, built fragment by fragment from the evidence preserved in the rock. Every bone tells a story. Every leaf impression says, "I was here, in the warmth, before the long winter came." The best places to find Antarctic fossils are the areas where the ice sheet has not completely covered the bedrock. The exposed rock outcrops along the Antarctic Peninsula, the Transantarctic Mountains, and certain coastal areas where the ice is thinner or absent. These outcrops are not numerous. Antarctica is roughly 98% covered by ice. The 2% that is exposed rock is doing an enormous amount of scientific work. Within those exposures, the sedimentary rock layers that were laid down in ancient rivers, lakes and coastal environments before the ice arrived are the prime targets. Sedimentary rock is where fossils form. The creatures die, are buried in sediment, and over millions of years their hard parts, bones, shells, wood, are replaced by minerals, slowly turning to stone in the shape of the original. Seymour Island, off the northern tip of the Antarctic Peninsula, is perhaps the most productive fossil site in Antarctica. It has yielded an extraordinary diversity of ancient life. Marine invertebrates from the Cretaceous period, including ammonites and mollusks, of the bones of mosasaurs, the giant marine reptiles that dominated the late Cretaceous seas, early whale relatives from the Eocene, and the small mammal fossils, including those ancient marsupials, that established beyond any doubt that warm-blooded, fur-covered, live birth-giving creatures once lived on Antarctic land. Each new field season at Seymour Island produces new specimens. The rock has not given up all its secrets. The Transantarctic Mountains, which run for over 3,000 kilometres across the continent, have produced some of the most dramatic finds. The Jurassic dinosaurs, including Cryolophosaurus. The fossilised forests in the Beardmore Glacier region, where petrified tree stumps still stand in their original growth position. Even an ancient fish fossils from freshwater lake deposits that speak of a time when rivers ran freely across the interior of the continent. Geologists working in these mountains work in some of the most remote conditions on Earth, living in small camps, operating in extreme cold and wind, carefully extracting specimens that will be transported in padded cases back to laboratories on other continents to be analysed. What drives someone to do this work? The conditions are brutal. The logistics are nightmarish. The pay is not, by any reasonable standard, commensurate with sleeping in a tent at -30, with a fossil femur as your most exciting possession of the week. Yes, but the thing that drives Antarctic paleontologists is the same thing that has driven every scientist who has ever walked into an unknown landscape with a hammer and a notebook. The certainty that something important is in there, waiting to be found. That the rock knows things the rest of the world doesn't yet know, and that if you are patient and careful and willing to be cold for a very long time, it will eventually tell you. The ancient world of Antarctica is still being read, fossil by fossil, season by season, bone by painstaking bone. One of the quietest and most extraordinary tools in the study of ancient Antarctica is pollen. Specifically, fossilized pollen, microscopic grains produced by plants that lived millions of years ago, preserved in sediment and rock, each one a tiny, virtually indestructible biological signature. Different plant species produce differently shaped pollen grains, and scientists who have spent enough time staring at them under microscopes can identify what kind of plant produced a given grain with remarkable precision. From pollen cores drilled from ancient Antarctic sediments, researchers have been able to reconstruct the vegetation of the continent at different points in its history. The types of trees that grew there, the shrubs that covered its hillsides, the mosses that carpeted its ancient wetlands. It is an astonishing level of detail to extract from something invisible to the naked eye, a portrait of a lost world written in dust. The scientific discipline of studying fossilized pollen is called palynology, and palynologists are a specific kind of person. They are people who have looked at enough microscopic pollen grains that they can tell, at a glance, whether a grain came from a conifer or a flowering plant or a fern or a moss, simply from its shape and surface texture. They can distinguish between dozens of species based on differences measured in micrometers. They spend long hours at microscopes, working through sediment samples one grain at a time, building a statistical picture of what plant community produced the pollen preserved in any given layer. It is methodical, painstaking, deeply specialized work. And in the case of Antarctica, it is some of the most revealing science that has ever been done on the continent. Pollen is extraordinarily durable. The outer coat of a pollen grain, called the exene, just is made of a substance called sporopollenin that resists chemical decay almost indefinitely under the right conditions. In Antarctic sediments that have been cold and dry and geologically undisturbed, pollen grains deposited tens of millions of years ago have survived in recognizable condition. You can drill a core from ancient Antarctic sediment, take a sample from a layer deposited 50 million years ago, process it chemically to extract the organic material, and find, under a microscope, pollen grains that are still identifiable by species. What those grains reveal is a detailed, time-stamped portrait of changing vegetation. In the earliest layers, the deepest, oldest sediments, the pollen tells of a warm, diverse flora, multiple tree species, ferns, flowering plants, and a rich community of vegetation occupying a warmer than today Antarctica. As you work upward through the sediment column, toward younger and younger deposits, the pollen changes. Warm-adapted species disappear. Cold-tolerant species become more dominant. The diversity decreases. The percentage of pollen from cold-adapted plants like southern beeches increases. And then, in the upper layers, the pollen disappears almost entirely, because the plants stopped growing, because the ice came. It is a story of loss told in grains too small to see without magnification, preserved by a chemical accident of biology, recovered by scientists willing to spend entire careers looking at things invisible to the naked eye. The ancient Antarctic landscape exists in those grains. The forest that stood on that continent for millions of years, the plants that grew through polar nights and photosynthesized in polar summers, the mosses and ferns and flowering plants that carpeted the ground between the trees, all of it is still there, in microfossil form in the sediment, compressed, preserved, waiting to be read. Somewhere in Antarctica, a sediment layer contains the last pollen grain ever produced by the last tree that ever grew there. One final grain from one final flower on one final day of warmth before the cold took everything. It is too small to see with the naked eye. It has been sitting in the dark for 30 million years. The freezing of Antarctica was not a clean, linear process. It did not simply get colder and colder until everything was ice. The Earth's climate does not work that way. Instead, the transition from a warm, vegetated Antarctica to the frozen continent of today was punctuated by warm spells and cold snaps, advances and retreats of ice, periods when the ice sheets shrank back significantly, and others when they expanded to cover nearly the entire continent. During some of these warmer interglacial periods, particularly during the Pliocene epoch, roughly 3 to 5 million years ago, global temperatures were only slightly warmer than today, perhaps 2 to 3 degrees Celsius on average, and yet the West Antarctic ice sheet may have collapsed partially or completely, contributing to sea levels that were perhaps 6 to 9 meters higher than they are today. Scientists study these ancient warm periods very carefully. They do this not out of academic curiosity, but because they tell us what is physically possible. And some of what is physically possible is quite alarming. The Pliocene is the period that keeps Antarctic climate scientists awake at night, and not just because they work in a field where insomnia is practically a job requirement. The mid-Pliocene warm period, roughly 3 million years ago, was the last time Earth's climate was consistently warmer than today over a sustained period. The atmospheric carbon dioxide concentration during the mid-Pliocene was similar to today's levels, around 380 to 400 parts per million. And the world was different. Sea levels were significantly higher. Arctic sea ice was reduced. The distribution of vegetation was shifted toward the poles, and the Antarctic ice sheets, particularly the more vulnerable West Antarctic ice sheet, appear, from the geological evidence, to have been considerably smaller than they are today. This matters enormously. If the mid-Pliocene, with carbon dioxide levels similar to today's, had sea levels 6 to 9 meters higher than today, then the question scientists are asking is, how long does it take for the ice to catch up to the atmosphere? The answer, based on everything we know about ice sheet dynamics, is longer than a human lifetime, but not longer than a civilization. The ice responds to warming slowly, because ice sheets are enormous and take enormous amounts of energy to melt. But once they begin to melt in earnest, the process accelerates, driven by the same kind of feedback loops that drove the original glaciation in reverse. Melting ice exposes dark rock and ocean, which absorbs more heat, which melts more ice. Oh, the warm spells in Antarctica's past were not anomalies. They were the normal behaviour of a climate system that oscillates, driven by changes in Earth's orbit, in solar output, in volcanic activity, in the composition of the atmosphere. The ice ages of the last 2.5 million years, the glacial and interglacial cycles that have repeatedly reshaped the northern hemisphere, are driven by subtle rhythms in Earth's orbit around the Sun, known as Milankovitch cycles. During glacial maxima, ice sheets expanded to cover much of North America and northern Europe. During interglacials, they retreated. Antarctica participated in these cycles too, expanding and contracting with the global rhythm of warming and cooling. And the lesson of these warm spells is not that the ice of Antarctica is fragile in the sense of being easily melted by a warm afternoon. It is not. The lesson is that the ice is sensitive to sustained warmth, to changed ocean temperatures, to the long, slow chemistry of the atmosphere. And that in the past, under conditions not dramatically different from those that exist today, significant portions of the Antarctic ice sheet have melted, raising sea levels to heights that would reshape every coastline on Earth. Buried under more than a mile of ice in Wilkes Land, a region of East Antarctica, there is an enormous circular feature roughly 480 kilometres across that some scientists believe may be the scar of a massive meteorite impact. Yeah, one that might be even larger than the Chicxulub impact that helped end the dinosaurs. This hypothetical impactor, if it existed, would have struck approximately 250 million years ago, right at the time of the Permian-Triassic extinction event, the largest mass extinction in Earth's history, which wiped out roughly 96% of all marine species and 70% of terrestrial vertebrate species. The connection between the two events, the putative impact and the extinction, remains scientifically controversial. Not all researchers are convinced the feature is an impact crater, but the fact that something of that scale may be buried beneath the ice of Antarctica, waiting to be properly studied, is a reminder that the continent has secrets that will take generations to fully uncover. The Permian-Triassic extinction event, which occurred approximately 252 million years ago, is known to geologists by a name that understates it considerably: the Great Dying. 96% of all marine species, 70% of all land vertebrates, gone in a geological instant. The cause, or causes, are still debated. Massive volcanic eruptions in what is now Siberia, the Siberian Traps, a flood basalt event of almost incomprehensible scale, almost certainly played a central role, releasing enough carbon dioxide and sulfur dioxide to acidify the oceans and destabilize the global climate catastrophically. But some researchers have pointed to the Wilkes Land anomaly as a possible contributing factor, a second blow, simultaneous or near simultaneous, that compounded the devastation already being wrought by the volcanism. You're standing in imagination on the ancient coast of Gondwana, 252 million years ago. The world around you is already dying. The seas are warming and acidifying. The forests are struggling. The air carries a faint chemical sharpness from volcanic gases drifting from the north. And then, from space, something arrives. You would not see it coming with any useful warning. The impactor, if the Wilkes Land feature is indeed an impact crater, and it is worth emphasizing again that this remains scientifically contested, would have been travelling at tens of kilometres per second. The impact would have released energy equivalent to billions of nuclear weapons simultaneously. The shock wave would have travelled through the Earth's crust. Your rock would have been vaporized. The Antarctic sky would have gone dark with ejecta. And the already struggling ecosystems of the Permian world would have faced a second catastrophic blow on top of the first. The evidence for the Wilkes Land feature comes primarily from satellite gravity measurements, subtle variations in the Earth's gravitational field that reveal density anomalies in the crust below. A large impact crater leaves behind a characteristic pattern, a zone of lower density fractured and melted rock, surrounded by a rim of compressed material. The Wilkes Land anomaly shows a pattern broadly consistent with this. It also sits at roughly the right geological level to be contemporaneous with the Permian-Triassic boundary. But gravity anomalies can have other causes, and without direct drilling through the ice to recover actual impacted rock, shocked quartz, spherules, iridium anomalies, the impact hypothesis remains exactly that, a hypothesis. What makes this story so compelling is precisely its inaccessibility. The potential answer to one of the most important questions in the history of life on Earth may be sitting under 2 kilometres of Antarctic ice, waiting. We cannot easily get to it. We may not be able to confirm or rule it out for decades. The ice keeps its secrets thoroughly. This one, if it is a secret at all, is buried deeper than most. The first humans to see Antarctica did not arrive until the early 19th century, which makes us extraordinarily late to the party. By the time European explorers finally crossed the Antarctic Circle and caught their first glimpse of the frozen continent around 1820, depending on which expedition's claim you accept, the ancient world of warm Antarctica had been buried under ice for tens of millions of years. The explorers who came first were not scientists. They were sealers and whalers, hard-bitten men who had no particular interest in geological history and every interest in not dying in the Southern Ocean. But the scientists followed, and when they began drilling and sampling the Antarctic rocks in earnest in the 20th century, what they found rewrote the history of the continent and of the Earth itself. Fossils that no one expected. Rock formations that told stories of a warm, living world. Evidence preserved in stone. That Antarctica was once the most alive it would ever be, and that the ice came for it anyway. The discovery of Antarctica itself is a story tangled in competing national claims. 3 expeditions, 1 British, 1 American, and 1 Russian, all claim priority for first sighting the continent in 1820. Edward Bransfield, an Irish-born officer in the British Royal Navy, is credited by some with the first confirmed sighting of the Antarctic Peninsula. Nathaniel Palmer, an American sealer from Connecticut who was barely 21 years old at the time, made his own sighting shortly after. Fabian von Bellingshausen, commanding a Russian Imperial Navy expedition, is credited by others with the first definitive sighting of the Antarctic continent itself. All 3 happened within the same narrow window of months, and the argument about priority has been simmering in the footnotes of Antarctic history ever since. Nobody has fully resolved it. Everyone involved was, by any standard, extraordinarily brave, sailing in wooden ships through waters that were trying very hard to kill them. The sealers who followed these first sightings were not explorers in any romantic sense. They were commercial hunters, and they were extraordinarily efficient. Within a few decades of the continent's discovery, the fur seal populations of the sub-Antarctic islands had been reduced to near extinction. The hunters stripped beaches bare and moved on. Their logs and journals, preserved in maritime archives, are some of the earliest detailed records of the Southern Ocean, records of weather, of ice conditions, of the distribution of wildlife. Written by men who cared nothing for science, but who observed the natural world with the sharp attention of people whose lives depended on that observation. The scientific expeditions came in waves. The heroic age of Antarctic exploration, roughly 1895 to 1922, sent multiple national expeditions to the continent. Belgian, British, Swedish, Norwegian, German, Australian, Japanese, each contributing to the growing understanding of what Antarctica actually was. The geologist among them began to find the first fossils. Plant fossils in the transantarctic mountains, marine fossils on the coasts, the first inklings of a warm past visible in the rock, completely at odds with the frozen world around them. Edward Wilson, the naturalist on Scott's ill-fated Terra Nova expedition, collected fossil plant specimens from the transantarctic mountains. Those specimens were found with the bodies of Scott and his companions. Wilson had carried them to the end, adding weight to a sledge that was already too heavy on a journey that was already too desperate. He carried fossil evidence of Antarctica's warm past through the cold that killed him. Science sometimes costs everything, and it carries its findings anyway. Antarctica today is not static. This is one of the things that surprises people most. The impression of Antarctica as frozen, permanent, eternal. But the ice is moving. It is always moving. glaciers flow slowly but measurably from the high interior plateau toward the coasts. Ice shelves, the floating extensions of the ice sheet that hang out over the ocean, calve, off icebergs in events that can be literally the size of small countries. The West Antarctic ice sheet, which sits on bedrock that is in places below sea level, is particularly vulnerable to warming ocean water eating away at its base. Scientists monitoring Antarctica today are watching processes that, if they continue, could raise global sea levels by meters over the coming centuries. The ancient world of warm Antarctica is not just history, it is a warning. The ice that buried an entire living world was built by the same basic mechanisms: changes in temperature, changes in ocean circulation, changes in the composition of the atmosphere that are now, in reverse, beginning to dismantle it. The movement of glacial ice is not fast by any measure a human would naturally use for speed. The fastest glaciers in Antarctica move at rates of a few kilometers per year. Most move considerably slower, but speed is not the point. The point is that the movement is continuous, relentless, and cumulative. Every year, ice that fell as snow on the high Antarctic plateau hundreds or thousands of years ago makes its way a little further toward the coast. Every year, a little more of that ancient ice carves off into the Southern Ocean as icebergs and slowly melts. This is the normal rhythm of the ice sheet. Snow accumulates in the interior, ice flows toward the margins, ice carves into the ocean, snow accumulates again. Under stable conditions, the system is roughly in balance. What scientists are currently measuring is an imbalance. More ice is leaving the margins than snow is replacing in the interior. Beneath the ice sheet, the subglacial hydrology we discussed earlier is not merely a static feature of the landscape. It is a dynamic system that actively influences how the ice sheet moves. Subglacial water acts as a lubricant, reducing the friction between the ice and the bedrock, and allowing ice streams, the fast-moving rivers of ice within the slower-moving ice sheet, to accelerate. When a subglacial lake drains suddenly, routing water downstream through the subglacial network, the ice above it can sink measurably, and the ice downstream can accelerate, sometimes dramatically. These subglacial flood events have been detected by satellite altimetry, scientists watching the surface of the ice sheet rise and fall by centimeters as water moves beneath it, from space, with instruments sensitive enough to detect the breathing of a continent. The icebergs carving from Antarctica's glaciers and ice shelves are monitored continuously by satellite. The largest of them, the ones that make the news when they break off, are given designations by the US National Ice Center. Labelled by the quadrant of Antarctica they originated from and a sequential number. Iceberg A76, which carved from the Ronne ice shelf in 2021, was approximately 4,320 square kilometres in area, larger than the island of Majorca, larger than the state of Rhode Island, floating freely in the Southern Ocean. A piece of ice the size of a small country, broken off from a continent, drifting north to melt. The ice is moving. It has always been moving. As to the question that the present generation of Antarctic scientists is trying to answer is whether the movement is accelerating in ways that cross thresholds, that trigger feedbacks, that set in motion processes, the ancient past tells us are very difficult to reverse. The ice does not wait for the answer. It moves at its own pace, carrying its ancient secrets toward the sea. In 1985, scientists from the British Antarctic Survey published a paper that sent shockwaves through the international scientific community. They had discovered a massive hole in the ozone layer directly above Antarctica, appearing each spring and large enough to cover the entire continent. The discovery came as a surprise even to the scientists who made it. Their instruments had been recording unusually low ozone values for years, but the data had been flagged as possibly anomalous and not fully processed. When they finally sat down and looked at the numbers properly, the hole was unmistakable. The cause was human-produced chlorofluorocarbons, the same chemicals used in refrigerators and aerosol cans, reacting with ice crystals in the Antarctic stratosphere to break down ozone with extraordinary efficiency. The ozone hole became one of the defining environmental stories of the late 20th century and, ultimately, one of the rare cases where humanity identified a global environmental problem and actually did something about it. The chemistry behind the ozone hole is specific to Antarctica, in a way that makes the continent's geography and climate uniquely vulnerable. During the Antarctic winter, the stratosphere above the continent becomes extraordinarily cold, but cold enough to form polar stratospheric clouds, thin veils of ice crystals at altitudes of 15 to 25 kilometers. These clouds provide a surface on which the chemical reactions that destroy ozone can take place efficiently. When spring arrives and sunlight returns to Antarctica, it triggers an explosive release of chlorine atoms from the chlorofluorocarbon molecules that have accumulated in the stratosphere, and those chlorine atoms begin destroying ozone molecules in a catalytic chain reaction, each chlorine atom capable of destroying tens of thousands of ozone molecules before it is eventually deactivated. The practical consequences of the ozone hole were real and immediate. Ozone in the stratosphere absorbs ultraviolet radiation from the sun. Without it, UV levels at the surface increase dramatically. For the ecosystems of the Southern Ocean and the Antarctic coast, this meant increased UV exposure for the phytoplankton and zooplankton that form the base of the marine food web. For the people living and working in southern South America, Australia and New Zealand, countries that sit beneath the seasonal edge of the ozone hole, it meant increased risk of skin cancer and eye damage during the Antarctic spring. Skin cancer rates in these regions, particularly in southern Chile and Argentina, were measurably elevated during the worst years of the ozone hole. The international response, formalised in the Montreal Protocol of 1987, was remarkably swift by the standards of global environmental policy. The production of chlorofluorocarbons and other ozone-depleting substances was phased out across most of the world within a decade. It is, by a considerable margin, the most successful international environmental agreement ever implemented. The ozone layer is recovering slowly but measurably, and current projections suggest that the Antarctic ozone hole will return to pre-1980 levels sometime in the second half of this century. The ozone hole story matters to the story of ancient Antarctica in an indirect but important way. It demonstrated with brutal clarity that the atmospheric chemistry of the planet can be changed rapidly by human activity, and that the effects of those changes can be concentrated over Antarctica in ways that are not immediately obvious from anywhere else on Earth. The continent is not an isolated, hot, passive landscape. It's connected to the global atmosphere, to the global ocean, to the global climate in ways that make it a uniquely sensitive indicator of planetary change. What happens in the stratosphere above Antarctica is felt in the markets of Melbourne and the beaches of Tierra del Fuego. The bottom of the world is closer to everything else than it looks. That is either comforting or alarming, depending on what is currently happening at the bottom of the world. In the end, Antarctica is not just a place, it is a record, the most complete climate archive on the planet, written in ice, preserved in rock, locked in sediment at the bottom of the Southern Ocean. Every ice core tells us something about the air that existed when the ice formed. Every fossilized tree stump tells us about a world that was warm enough to grow a forest at the bottom of the Earth. Every subglacial lake tells us about the hidden complexity of a continent that, from the outside, looks like nothing but white silence. The story of Antarctica, from its warm forested beginnings as part of Gondwana, through its slow freezing, through the burial of everything that once lived there, to the extraordinary scientific station it has become today, is ultimately a story about time. about how long the Earth has been here, and how much it has changed, and how much it is capable of changing again. That is the thing the ancient world of Antarctica whispers, if you know how to listen. It has been here before, the warm, the cold, the ice, the thaw, and it will decide with or without us what comes next. There is a specific quality to the silence of Antarctica that people who have been there describe in almost identical terms, regardless of their background, their nationality, or their reason for being there. It is not merely the absence of sound, though that is part of it. It is the presence of something deeper than sound, a silence so complete that it has weight, that it makes the sounds you do hear, the creak of a boot on packed snow, the distant groan of a glacier shifting, the wind against the fabric of a tent seem extraordinarily vivid and significant. Scientists who have worked in Antarctica for a season often describe it as the most clarifying experience of their lives. Not comfortable, not easy, but clarifying. A place where the noise of ordinary existence is stripped away, and what remains is rock and ice and sky, and the particular quality of attention that comes from being somewhere that will kill you if you stop paying it. That quality of attention is, in a sense, what Antarctica demands of the scientists who study it. The work is slow, difficult, cold, and expensive. The payoff is not immediate. A paleontologist who spends a season searching for fossils on an Antarctic rock outcrop may return with a few fragments of bone and a great deal of frostbite, and spend the next 2 years analysing what those fragments mean. An ice core driller may spend months in the field for a few metres of core that will take years to fully analyse. The science of Antarctica is not the science of quick results. It is the science of deep time. And deep time requires a different pace, a different relationship with results and certainty and the satisfaction of knowing. What Antarctica tells us about ourselves is something similar. We are a species that has existed for roughly 300,000 years on a planet that has existed for 4.5 billion. We have been building civilizations, in any meaningful sense, for perhaps 10,000 years. In the context of Antarctica's history, the warm Gondwana world, the ancient forests, the long freezing, the ice sheets, the hidden lakes, the ancient brine, our entire recorded history is a rounding error, a thin layer in the sediment column, and yet we have in that thin layer changed the chemistry of the atmosphere in ways that are legible in the same record that preserves the history of everything else. Antarctica is not indifferent to this. Nothing about the planet is indifferent. It responds according to its physics, according to its chemistry, according to the slow and powerful logic of systems that have been running for billions of years. The ancient warm world that lies under the ice was not permanent. The ice that replaced it was not permanent. Nothing about this planet is permanent, except the fact of change itself. Antarctica has survived everything that has ever happened to it. The question the ancient ice is quietly asking is whether we have been paying attention. Let's talk about the one place in Antarctica where the ice gave up. Not because it was warm enough. Nothing about this place is warm, but because the physics simply didn't cooperate. The McMurdo Dry Valleys, tucked into the Transantarctic Mountains in Victoria Land, are the largest ice-free region on the Antarctic continent. They're also, depending on your tolerance for extreme desolation, either the most fascinating or the most unsettling landscape on Earth. The glaciers that flow from the polar plateau are blocked by the mountains, and the cold, dry winds that race down the valleys evaporate any snow before it can accumulate. The result is a landscape of bare rock, frozen soil and ancient lake ice, sitting open to the Antarctic sky like something scraped clean by an enormous and indifferent hand. No ice sheet, no snow cover, just rock and wind and silence so complete it has a texture. You're walking across the floor of the Taylor Valley. The ground under your feet is not soft. It is a mix of gravel, sand, and rock fragments, frozen solid, cracking faintly under your boots. The colour is extraordinary. Rust reds, dark greys, ochre yellows. Because without ice to cover it, the ancient Antarctic bedrock is exposed in its full geological complexity. The landscape has an almost Martian quality to it, which is not an accident and not just a poetic observation. It is a documented scientific parallel. To your left, a glacier tongue pushes down from the valley wall, its blue-white face cracked with deep crevasses, stopped in its tracks by the same katabatic winds that keep this valley clear. Ahead of you, Lake Bonny sits sealed under a permanent lid of ice several metres thick, its liquid water hidden beneath, home to microbial communities that have been living in those cold, chemistry-rich depths for thousands of years. The dry valleys are among the coldest and driest deserts on Earth, when annual precipitation is less than 10 centimetres, almost all of it as snow that sublimes before it can accumulate. Temperatures in winter drop to minus 40 degrees Celsius and below. In summer, they occasionally climb above freezing for a few weeks, long enough for thin streams of glacial meltwater to run briefly across the valley floors before freezing again. These streams support simple algal communities during their brief existence, mats of cyanobacteria and other microorganisms that photosynthesize furiously during the few weeks of liquid water, then freeze in place and wait for next year. If you scraped up a piece of this frozen algal mat and examined it under a microscope, you would find organisms that are not dead but dormant, suspended waiting for the warmth to return. The ancient history of the dry valleys is not the ancient history of the forests. They were ice-covered for much of the period when forests grew elsewhere on the continent. But during warmer periods in the more recent geological past, including parts of the Pliocene, the valleys held larger and deeper lakes than they do today, fed by more substantial glacial meltwater. Sediment cores from beneath the modern lake ice reveal layers of organic material, diatom fossils, and chemical signatures that speak of warmer, wetter conditions alternating with colder, drier ones over hundreds of thousands of years. The valleys have been an oscillating environment, repeatedly thawing and freezing as the climate swung through its cycles, and the microbial communities that live there today are the descendants of organisms that have survived every one of those swings. NASA uses the dry valleys as an analogue for Mars, not casually but methodically, sending instruments there to test how they will perform on the Martian surface, using the valley environments to calibrate models of Martian habitability. The logic is sound. If life can survive in the dry valleys, under conditions that bracket the range of what Mars may once have offered, then the search for life on Mars is not a fantasy. The ice gave up on the dry valleys. The life there did not return the favour. There is a waterfall in Antarctica that runs red. Not metaphorically red, not slightly pinkish or vaguely orange, genuinely, unmistakably, deeply red. The colour of old iron, of rust, of something that looks, in the white and blue and grey world of the Taylor Valley, entirely wrong. Blood Falls, as it is straightforwardly named, seeps from the snout of the Taylor Glacier and stains the ice and snow around it in a vivid crimson streak that has been unnerving scientists and visitors since it was first described in 1911. The explorer Griffith Taylor, for whom the glacier and valley are named, initially assumed the red colour was caused by algae. He was not entirely wrong in spirit, but the full explanation, which took the better part of a century to work out, is considerably stranger and considerably more interesting than algae. Beneath the Taylor Glacier, sealed under the ice at a depth of several hundred metres, is a pocket of ancient brine, a highly salty liquid so cold that its freezing point is pushed well below the temperature of the surrounding ice, allowing it to remain liquid in conditions that would freeze ordinary water solid. This brine has been isolated from the surface for an estimated 3 to 5 million years. It is a remnant of an ancient marine inlet that was sealed when the glacier advanced over it during the Pliocene cooling. Cut off from light, from oxygen, from any contact with the surface world, the brine has been quietly doing its own chemistry ever since, developing a composition unlike almost anything else on Earth: hypersaline, anoxic, rich in dissolved iron, and cold enough to make your teeth ache just thinking about it. The red colour that gives blood falls its name is the result of what happens when this ancient and iron-rich brine finally reaches the surface and meets air. The dissolved iron compounds in the brine, which have been in an oxygen-free environment for millions of years, react instantly with the oxygen in the atmosphere and oxidize. They rust. What you're seeing seeping down the face of the Taylor Glacier and pooling on the ice below is essentially the same process that turns iron red in the open air, oxidation, the combination of iron with oxygen, except that in this case the iron has been waiting, sealed in a pocket of ancient salty water for 3 to 5 million years to encounter its first oxygen molecule. It is one of the most dramatic chemical reactions on Earth, and it happens on a frozen glacier at the bottom of the world. The microbes living in the Bloodfalls brine are perhaps the most extreme example of life on Earth. They have no light. They have no oxygen. They are under pressure in extreme cold, in water so salty that most organisms would desiccate instantly upon contact with it. They metabolize sulfate compounds and ferric iron in a process that extracts energy from chemistry rather than from sunlight. A metabolic strategy called chemolithotrophy, which sounds like something invented for a science fiction novel, but is a real and well-documented form of life that exists in deep-sea vents, acid mines, and apparently in pockets of ancient brine beneath Antarctic glaciers. These microbes are not just curiosities, they are existence proofs. Proof that life can sustain itself in conditions that, before their discovery, would have been considered incompatible with biology. Every time science finds life somewhere it was not expected, in hypersaline brines, in superheated volcanic vents, in the crushing darkness of deep Antarctic ice, the universe of places where life might conceivably exist gets a little larger. Bloodfalls looks like Antarctica is wounded. It is not wounded. It is revealing something extraordinary from very deep inside itself, in the only colour it has available. Red, as it turns out, is the colour of 3-million-year-old persistence. Around the edges of Antarctica, where the ice sheet meets the ocean, something extraordinary happens. The ice does not simply stop at the coastline. It keeps going. It flows out over the water and continues floating, forming vast, flat platforms of ice, some of them the size of France, that extend for hundreds of kilometres over the Southern Ocean. These are the ice shelves, and they are among the most dynamic, most consequential, and most rapidly changing features on the Antarctic continent. The largest of them, the Ross Ice Shelf, is roughly 590,000 square kilometres, a floating slab of ice averaging about 330 metres thick, sitting on top of the ocean like a frozen lid, its seaward edge a cliff of ice rising 30 metres above the water and extending another 250 metres below the surface. Amundsen, the first man to reach the South Pole, called it the Great Ice Barrier. Standing at its edge, in the open Southern Ocean, with nothing but a wall of ice in front of you and nothing but sea behind, it is not hard to understand why. Let's talk about what it actually feels like to stand at the edge of a large ice shelf. The cliff face in front of you is not white the way snow is white. It is the white of something dense and ancient, with a faint blue tint in the deeper layers where the ice is compressed beyond a certain point, and the air bubbles that scatter white light have been squeezed out. The face of the cliff is not smooth. It is fractured and grooved, carved by wind and meltwater into irregular shapes, and at the waterline it has been undercut by the sea, so that the top of the cliff overhangs the water slightly, and if you watch long enough, you'll see chunks of ice carving from the face and dropping into the ocean with a sound like distant artillery. This is normal. This is the ice shelf doing what ice shelves do, which is slowly, continuously carving icebergs into the sea. The ice shelves act as buttresses for the glaciers that flow into them from the continent behind. This is the thing that makes them so consequential from a sea level perspective. The glaciers of the Antarctic interior are always flowing toward the coast, driven by the weight of the ice behind them. The ice shelves, floating but attached to the coastline, provide resistance, a physical barrier that the glaciers must push against before their ice can reach the open ocean. Remove the ice shelf, and the glaciers behind it accelerate, pouring ice into the ocean faster than before, contributing directly to sea level rise. This is not theoretical. The collapse of the Larsen B ice shelf in 2002, roughly 3,250 square kilometres of ice that had existed for at least 10,000 years, disintegrating in 40 days. Was followed within months by the accelerated flow of the glaciers that had fed into it. Some of those glaciers moved up to 8 times faster after the shelf was gone. The ice that had been held back began flowing into the ocean. The sea level response was small but measurable, and the scientific implications were enormous. The ancient ice shelves of warmer periods, the Pliocene, the Eocene, were smaller or absent entirely. The geological record of those warm periods includes the evidence of higher sea levels that resulted from the loss of ice shelf buttressing, the acceleration of glaciers, and the eventual collapse of parts of the West Antarctic ice sheet. It happened slowly by human standards, but it happened. The ice shelf is holding something back. That is quite literally its job. It has been doing that job for millions of years. Klecks. The question scientists are currently asking with data and models and genuine urgency is how much longer it intends to keep doing it. Let's take a moment to go to the place that started the most famous race in the history of exploration, the geographic South Pole. Not the magnetic South Pole, which wanders around and is currently sitting somewhere off the coast of Antarctica in the Southern Ocean, apparently unwilling to commit. The geographic South Pole, the actual bottom of the Earth's rotational axis, 90 degrees south, the point where every direction is north. It sits on the East Antarctic ice sheet at an elevation of roughly 2,835 metres above sea level, which means you're standing on nearly 3 kilometres of ancient ice, with the actual bedrock of Antarctica somewhere far beneath your feet. The air is thin, the cold is serious, and above you the sun traces a flat circle around the sky, without setting for 6 months, then vanishes completely for the other 6. There is a marker here, placed by the United States Antarctic Program, moved every year on New Year's Day to correct for the flow of the ice sheet, which carries it slightly away from the actual pole annually. Even the bottom of the Earth is technically moving. You're standing at 90 degrees south. Every direction from where you are standing is north. This is not a metaphor, it is a geometrical fact. If you start walking in any direction whatsoever, you will be walking north. The concept of south ceases to have any meaning at the South Pole, in the same way that the concept of west ceases to have meaning at the North Pole. Compasses at the pole point in the direction of north, which is every direction, and therefore give you exactly no useful information about where you're going. Early explorers navigating by compass had to correct for this by using celestial observations, measuring the position of the sun at known times to determine direction, rather than relying on the magnetic needle that worked everywhere else on Earth. The cold at the South Pole is its own category of cold. The average annual temperature at the Amundsen Scott South Pole Station is approximately minus 49 degrees Celsius. In winter, temperatures regularly drop below minus 60, occasionally below minus 70. At these temperatures, exposed skin freezes in seconds, metal becomes brittle, fuel thickens, rubber gaskets fail. The moisture in your breath freezes immediately upon exhalation, producing the faint crystalline haze that Antarctic workers call diamond dust, ice crystals so small and light they float in the air rather than falling. Breathing deeply at the South Pole feels like inhaling something that is trying to damage you on the way in. It is, in that specific and physical sense, accurate. Roald Amundsen arrived here on the 14th of December 1911, after a journey of 99 days from the Bay of Whales. He planted a Norwegian flag and named the polar plateau the King Haakon VII Plateau. His team spent 3 days at the pole taking measurements, confirming their position by multiple methods, and leaving a small tent with a note addressed to the King of Norway, and, in a gesture of extraordinary composure, to Robert Falcon Scott, asking him to forward the letter to the King in the event that Amundsen's team did not return. Amundsen was, among other things, meticulous. Scott arrived 34 days later. He found Amundsen's flag. He found the tent. He found the note. He took a photograph that is one of the most famous and most heartbreaking images in the history of exploration. 5 men at the South Pole having lost the race they came to win, knowing the return journey still lay ahead of them. None of them made it back. The South Pole rewards the prepared. It has very little patience for anything else. Let's end where the science gets genuinely urgent. Not alarmist, the story of Antarctica is, above all things, a story about time, and time is the one thing that geological history teaches you to hold carefully and without panic. But honest. Because the ancient warm world of Antarctica that we have spent this entire journey exploring is not just history. It is, in a very specific and well-documented scientific sense, a preview. A before photograph. A record of what this continent looked like the last time the atmosphere contained the levels of greenhouse gases that it is approaching now. And what that record shows us, written in ice cores and fossil pollen, and ancient sea levels carved into coastal rock on other continents, is that the Earth under these conditions is capable of significant, sustained, and eventually irreversible change. The ice of Antarctica has melted before, not all of it, not quickly, not in a human lifetime, but enough of it, sussed over enough time to raise the oceans of the world by meters. That is the conversation the ancient past is trying to have with us. The distinction between geological time and human time is the most important thing to hold in mind when thinking about the future of Antarctica. On geological time, ice sheets grow and collapse routinely. On human time, they appear permanent. The challenge of Antarctic science right now is to bridge those two timescales, to take the information encoded in ancient ice and rock and sediment, and translate it into projections that are meaningful on the scale of decades and centuries, the scale on which human societies actually make decisions. This is not a simple translation. The geological record is good at showing what happened over thousands and millions of years. It is less good at showing exactly how fast things happened, because the resolution of most geological archives is not fine enough to distinguish between a change that took 100 years and one that took 1,000. What the record does show, with increasing clarity, is that ice sheet changes can be abrupt. The collapse of the Larsen B ice shelf in 40 days is a modern example. The geological record contains evidence of ancient sea level jumps, called meltwater pulses, that suggest very rapid ice sheet collapses in the past, potentially raising sea levels by meters in centuries rather than millennia. Meltwater pulse 1A, which occurred approximately 14,600 years ago at the end of the last ice age, has raised global sea levels by roughly 14 to 18 meters in a period of perhaps 300 to 500 years. Not all of that came from Antarctica. The Northern Hemisphere ice sheets contributed substantially, but the event demonstrates that the climate system is capable of rapid, large magnitude changes in ice volume and sea level. The Thwaites Glacier is the place where these abstract concerns become concrete. It is currently losing ice at an accelerating rate. The warm ocean water circulating beneath its floating ice tongue is melting it from below. Its grounding line, the boundary between the glacier and the bedrock, is retreating. The ice shelf that was partially buttressing it is fracturing. Scientists studying Thwaites have described a range of possible futures, from gradual ongoing loss to scenarios involving more rapid destabilization over the coming decades and centuries. The uncertainty is real, but the direction, more ice loss, higher sea levels, continued change, is not. And yet Antarctica has been here before. It survived the Great Dying. It survived the opening of the Drake Passage. It survived 34 million years of glaciation. It will survive whatever the next chapter brings. The question is not whether Antarctica will be all right. It will be on its own timescale, in its own way, with or without the ice. The question is what we will be, on ours. The ancient forests are down there, under the ice, in the rock. The dinosaurs are down there. The warm, shallow seas are down there, fossilized and waiting. The entire extraordinary, improbable, vanished world of warm Antarctica is down there, patient and permanent, teaching anyone willing to listen that nothing about this planet stays the same forever. Not the warmth, not the cold, not the ice, not us. Everything changes. The only question is what we do before it does. And so, here we are, at the end of a journey that began in a warm, green, impossible world at the bottom of the earth and travelled all the way to the ice-covered, ancient, extraordinary continent that replaced it. You have walked through Gondwana forests that no human eye has ever seen. You have stood on beaches that disappeared 30 million years ago. You have heard the last trees falling silent under the first snow that never melted. You have floated above subglacial lakes that have been dark and sealed and quietly alive for longer than our entire genus has existed on this planet. And now, as you lie in your warm bed, in your heated home, with clean water running from a tap and food in a refrigerator that is not, thankfully, the size of a continent, take a moment, just a quiet moment, to think about the people who drilled through 2 kilometers of ice in temperatures that could kill you in minutes, just to hold a piece of ancient air in their hands, who crawled across wind-blasted rock outcrops looking for a fragment of fossilized bone, who sailed wooden ships into the most violent ocean on Earth because something was down there, at the bottom of the world, and it needed to be known. They were stubborn, they were curious, they were frequently very cold, and because of them, we know what Antarctica looked like before the ice. We know it was alive. We know it was warm. We know it was full of forests and creatures and rivers and the same kind of improbable, persistent, beautiful life that is right now, asleep in your bed. The ice buried a whole world once, and the world kept going anyway. So can you. Good night, sleep warm, and thank you, genuinely, for spending your night with Snoozy Voyager.